In the summer of 1982, in a handful of towns in Northern California, several people bought the same new drug. They injected it. It worked the way they expected it to. Then, over the next few days, each of them began to slow down. Not tired. Not weak. Slow. Their arms took longer to answer. Their faces stopped moving. Within a week, some of them could not speak, could not walk, could not lift a hand to their own mouths. They were awake the entire time. They could hear every word said in the room. Something in that drug had found a structure deep in the middle of their brains, a patch of dark tissue about the size of a postage stamp, and destroyed it. The first one arrived in July. His name was George Carillo. He was 42 years old, and he was brought to Santa Clara Valley Medical Center in San Jose, California, from a nearby jail. He was admitted to the locked psychiatric unit with a diagnosis of catatonic schizophrenia. It was a reasonable guess. He sat where he was put. He did not speak. He did not react. When staff moved his arm, it stayed exactly where they left it, held in the air, until someone moved it again. The neurologist on service that month was the hospital's director of neurology, a physician named William Langston. He was in his office with a cup of coffee and a stack of tests to read when the chief resident called him and said something he later wrote down almost word for word. "I've never seen anything like it, and no one is sure what this patient has." Downstairs, an argument was underway. The psychiatrists were convinced the problem was neurological. The neurologists were convinced it was psychiatric. Both teams were looking at the same man, and neither could make him fit. Langston went down and examined him, and within a few minutes knew the psychiatrists were right about one thing. This was not catatonia. There is a specific thing an experienced neurologist does when a patient will not move. You take the wrist or the elbow and you bend it, and you pay attention to what pushes back. In catatonia, the resistance is irregular. It comes and goes. It feels like a person deciding, somewhere underneath, to resist you. That is not what Langston felt. What he felt was smooth, constant, and mechanical. A limb that gave way in small, even steps like a ratchet turning. Doctors have a name for this. They call it cogwheeling because that is exactly what it feels like. Teeth catching, one after another, all the way through the movement. There is one disease that does this. And George Carillo had every other feature of it. The mask-like face. The stooped posture. The complete absence of the small, automatic movements that a body makes without being asked. He looked, Langston later wrote, like a textbook case of advanced Parkinson's disease, the kind you would have seen in a hospital ward before there was any treatment for it at all. Except that Parkinson's disease is a disease of decades. It arrives quietly in one hand, in a slight tremor, in handwriting that gets smaller. It takes years to reach the state George Carillo was in. And Parkinson's disease overwhelmingly arrives after 60. George Carillo was 42. And by his own account, once they finally found a way for him to communicate, this had happened to him in a matter of days. A single case like that is a curiosity. What happened next made it something else. Langston went looking. He alerted local media. He worked with police. And over a remarkably short period, 6 more patients surfaced with the same thing: frozen, rigid, awake, young. They were not one group of friends. Several of them lived in different towns and had never met. There was no shared meal, no shared building, no shared workplace. There was exactly one thing connecting them. In the weeks before it happened, every one of them had used the same new synthetic heroin sold on the street in Northern California, part of what was then being called the designer drug phenomenon. Chemists making analogs of controlled substances, one molecule off, to stay ahead of the law. Through police seizures and a few cooperative dealers, samples came in. And when they were analyzed, one batch was not really heroin at all. It was almost pure MPTP. MPTP was not the drug anyone was trying to make. The intended product was a synthetic opioid, a meperidine analog first made in a laboratory in 1947 and never commercialized, which meant it had never been regulated. MPTP was a byproduct. Get the temperature wrong, rush the reaction, and instead of the opioid you get a contaminant. It had no street value. It was an accident of chemistry, and it was in the syringe. But here is what makes this case different from a poisoning. This had already happened. 6 years earlier. On the other side of the country. and it had been published in a medical journal where anyone could read it. In 1976, a 23-year-old chemistry graduate student named Barry Kidston decided he could make his own opioid rather than buy one. He had the training. He found the 1947 synthesis. He made it in his own apartment and injected it. Within days he could barely move. He was taken to the National Institutes of Health in Bethesda, Maryland. The doctors there recognized what they were looking at, a young man with full-blown Parkinsonism and no explanation for it. They treated him with levodopa, the drug that replaces the missing signal in Parkinson's disease. He responded. He got some of his movement back. They knew it had come from something he had injected. A chemist there named Sanford Markey worked on the samples. But the case was written up while the picture was still incomplete, and when it was published in the journal Psychiatry Research in 1979, the compound responsible was not named. Barry Kidston did not recover. In September of 1978, he died of a drug overdose. At autopsy, the same small dark structure, the one about the size of a postage stamp, had been destroyed. The paper sat in the literature for 4 years. The observation was correct. The patient was real. Nobody connected it to anything because there was nothing yet to connect it to. It took 6 more people frozen in California to make that paper mean something. Here is the part that made every neuroscientist in the world pay attention. MPTP itself is not a poison. Put it on a cell in a dish and the cell is fine. It does not attack tissue and it does not damage nerves. What it does have is one useful property: it dissolves in fat. And the barrier that protects your brain from most of what circulates in your blood is built of fat. So MPTP walks through a wall that stops almost everything else and arrives in the brain completely harmless. Then the brain does the rest. Inside the brain there are support cells, not neurons but the crew that maintains them, and they carry an enzyme whose ordinary job is to break down leftover signaling molecules. That enzyme takes MPTP and modifies it. What comes out the other side is a different compound, MPP+. And MPP+ is a poison. Now it is loose in the brain. And this is where the selectivity comes from, and it is genuinely strange. Dopamine neurons are thrifty. When they fire, they release dopamine into the gap, and then they pull most of it back into use again, through a dedicated port on their own surface. Think of it as a vacuum built into the cell wall, running constantly, reclaiming the cell's own product. MPP+ is shaped closely enough to dopamine that the vacuum accepts it. That is the whole mechanism of the selectivity. The poison had no way into those cells. The cells opened the door and pulled it in because it resembled the thing they exist to collect. Nearly every other cell in the brain is bathed in the same compound and survives, because it has no vacuum and never takes it up. Inside the neuron, MPP+ concentrates in the mitochondria, the structures that make the cell's energy. A mitochondrion runs something like an assembly line, with several stations in sequence, each handing off to the next. MPP+ jams the first station. Stop the first station and the whole line stops. The energy supply fails. And the cells with the vacuum, the dopamine neurons packed into that small dark structure in the midbrain, the substantia nigra, die. That structure is what lets you begin a movement without thinking about beginning it. When enough of it is gone, the intention to move survives completely intact, and the movement does not come. That is what the word frozen is doing in this story. It was never a metaphor. The patients were treated with levodopa and it worked, dramatically and almost immediately. People who had been unable to speak were able to speak. People who had been motionless for weeks got up. But the improvement came with the disease's own signature complication. Levodopa in Parkinson's disease eventually produces involuntary writhing movements, usually after years of treatment. In these patients it appeared fast. In one of them within 6 weeks. And the drug replaced the signal. It did not replace the cells. Those were gone and they do not come back. Langston's team published the 7 cases in Science. In February of 1983, Langston, Ballard, Tetrud and Irwin, identifying MPTP as the cause. He later described what happened the day it came out. Calls from researchers around the world, all asking the same question. Where can we get this compound? The paper had mentioned it was available from a chemical supplier. That supplier sold out within hours. When it came back in stock, the price had gone up roughly 100-fold. Because everyone wanted the same thing and it had never existed before. Parkinson's disease research had been stuck for a specific reason. There was no good animal model. You cannot study a disease you cannot reproduce. Within a year, in 1984, researchers had given MPTP to monkeys, and the monkeys developed the motor features of Parkinson's disease, responded to levodopa the way patients do, and on examination had lost the dopamine neurons of the substantia nigra, while the neighboring region was spared. Exactly as in the human disease. Langston put it in a line worth repeating. They now had the human model of the animal model of the human disease. 3 things followed from that. First, since blocking the converting enzyme stops MPTP from ever becoming a poison, researchers blocked it in primates and prevented the Parkinsonism entirely. That result opened the entire field of neuroprotection research in neurodegenerative disease, and the clinical trials it produced are still being argued about today. Second, and this is the one that reaches patients now. Because the primate model was stable and reproducible, Malin DeLong was able to use it to map the circuitry of the basal ganglia, and found that after the substantia nigra degenerates, a small structure called the subthalamic nucleus becomes overactive. Quieting it in those animals abolished the major motor features of their Parkinsonism. Alam Louis Benabid and colleagues later showed that you could do this in patients, not by destroying the structure but by placing an electrode in it. That is deep brain stimulation. It is now a standard treatment for Parkinson's disease, and the path to it runs directly through a contaminated batch of street drugs in 1982. Third, MPP+, the toxic metabolite, is nearly identical to paraquat, a herbicide used around the world. They differ by a single methyl group. And rotenone, another pesticide, jams the same first station of the same assembly line. That resemblance is a large part of why the environmental hypothesis of Parkinson's disease was taken seriously at all, and why pesticide exposure has been studied as a risk factor ever since. Between 5,000 and 7,000 scientific papers have been published on this compound. Langston's own conclusion, 35 years later, was not about chemistry. It was that the entire thing turned on one clinician walking downstairs to look at one patient who did not fit, and refusing to accept the label already on the chart. George Carillo spent an unknown number of days locked in a psychiatric ward, fully awake, being treated for a disease he did not have. The chart said catatonic schizophrenia. Every observation fit, until someone bent his arm. So here's the question. In that hospital, the wrong answer was already written down by competent people for defensible reasons. At what point would you have stopped believing the chart?